All right, welcome back from round two. So we'll continue with our idea of light. The problem is light, the way we thought about it, is just a wave wasn't good enough for what we were trying to do. Okay, and so Max Planck came up with this idea. If light were only a wave, as an object cools, it would have to lose energy continuously because waves a continuous amount. But it loses energy in certain amounts, which he called quantum, right? And we're going to talk about this idea of the photoelectric effect. So if I get me out of the way, if what we see is we see these energy waves come in, but we see these particles come off. And what he was saying is that if energy was only that wave, it wouldn't be able to happen that way. Okay, there's got to be something else that we're not seeing. There's got to be something smaller, something that's built in that wave, right? But because he noticed a certain quantum, we're going to be able to take a look at that. And so we have another fairly famous guy, right? That dude right there. And so Albert Einstein took that idea, and what he did is him and de Broglie, who we'll see a little bit later, came up with this dual nature of light, right? And what they said is light is both a wave and a particle. So basically, it's a wave that's built up of even smaller particles. All right. And so those particles they call photons, which maybe some of you have heard about before. And those photons are massless with a quantum of energy. So basically, he took Planck's idea and he gave them a size. And so these photons, these particles, have that same quantum of energy that Planck took a look at before. And what he determined even further is that those energies, those quantum, depends on frequency. Right, which frequency we saw in the last slide. So somehow we got to involve energy here. That's the whole title of this is we need to get energy in there. And so he comes up with this pretty nice equation, right? It looks very similar to the one we just saw. And so what Einstein did, and this is one of the reasons he won a Nobel Prize, is he said the energy of a photon is equal to this h, which we'll talk about in seconds, times this v-looking thing, which is new. We've dealt with that before, right? That's frequency. All right, so this one's pretty straightforward. So energy is measured in joules, right? So the energy of a photon is measured in something we call joules. H is a constant, so that actually makes this one pretty easy. And this is called Planck's constant. That's what Planck was talking about. So this is 6.626 times 10 to the negative 34th joules times seconds. Okay. And this is just something that you have to have access to. And then we have frequency again, right? Which we know is in hertz or 1 per second or second to the negative first. However we want to think about it. So we have two equations. We have C equals V times lambda or nu times lambda. And now we have this new one for energy, right? And so we want to be able to use both these equations as we go. And really what all of these guys figured out is this is a picture of the photoelectric effect in action. We have this wave coming in, and this is really what Bohr was doing too. He just didn't know it at the time, is this wave comes in, this particle of energy that is made up of photons with quantums of energy. Right, don't worry about all those words, right? But they come in and they knock this electron off. They excite it, which that is a word we're gonna talk about in a little bit, and they make it go somewhere else. They give it a Red Bull, right? They give it some energy and they say, hey, take this, see what you can do with it. And it's this is the part that we end up seeing with our eyeballs. Now, again, we're not going to be able to do the lab that's associated with this chapter, but I'm going to try to save it when we come back, and we'll come back to this and do it because it's a really good one. And no amount of filming will do it justice. So we'll take a look at this one later. But that's the idea of what we're trying to do, or how they proved these photons. So basically there's photons in this wave with a certain amount of energy, those quantum, and they are able to distort atoms' electrons. Okay. And so we could calculate this again. And so we're going to try to do that, and I'll bring that down. So again, we have this amount of energy, right? So given a hydrogen has a yellow spectral line with an energy of 3.43 times to the negative 19th joules per photon, but really we don't need that photon. We're first going to figure out the frequency, and then we're going to figure out the wavelength. All right. So I'm going to bring the visualizer back down. I'll show you one more. All right, so let's do this. So again, what do we know? We should always be writing that down. And so what we know is we have 3.43 times 10 to the negative 19th joules, right? And we know that to be energy. Great. It wanted us to find frequency. And we know frequencies that V, that nu. All right, so I'm going to put my question mark there. And then the other thing we know is with this equation of energy, we have this Planck's constant. And Planck's constant never changes. It's constant. So it's 6.626 times 10 to the negative 34th joules times seconds. Okay, so we're going to go look at our equation, which is E equals V times H. Doesn't matter what order that goes in, right? Rearrange it to find V. So V is equal to E divided by H. And now we can chuck in our numbers, right? So my E is 3.43 times 10 to the negative 19th joules, okay? And then I have 6.626 times 10 to the negative 34th joules times seconds. And what I end up with is, cross out in a different color, joules are gone. I'm left with seconds, but seconds are on the bottom. This is not a second, it's a per second, which is good because that guy being on the bottom is equal to a hertz, right? And so we can calculate this in units of hertz, which is good, and that's what we want to do. So if I put this into my calculator, right? So I have 3.43 times 10 to the negative 19th, okay? And I'm going to divide that by 6.626 times 10 to the negative 34th, okay? And again, this is where I'd highly suggest thinking about what you just put in your calculator to make sure you come up with the right answer, all right? We should have a positive exponent, and we do because we have a negative divided by a bigger negative. That gives us a positive. And so here we can write, using 3 sig figs because we have 3 and 4, 5.18 times 10 to the 14th. All right, there's question number 1 done. Not too bad. Question number 2 says, all right, what is the wavelength of that guy, right? And so we know wavelength is this lambda, right? I need to know that. And to find that, the equation we have is we have C and we have nu, right? And so I know that C is equal to lambda times nu. And in order to find that, which we discovered before, I take C divided by nu. Well, we already have that, right? We can take that guy and we can stick him in right down there. And then we just got to remember what C is. Well, remember, C is a constant. And so that is 3.00 times 10 to the 8th meters per second. All right, now we can put those numbers in. All right, and so my C is 3.00 times 10 to the 8th meters per second, divided by 5.18 times 10 to the 14th hertz, right? And really hertz over per second, they cancel each other. And so we put this in and we get about, all right, I'm not gonna put it in, I'm gonna save some time. We get about 580 nanometers. In our calculator, it would actually look like 5.80 times 10 to the negative 7th meters. Either of those is fine. Just trying to sum it up. And if we've looked at that, we'd have a yellow looking line, which is cool. All right. So the calculations aren't bad. You got to keep them straight. Okay. And so just to kind of finish this off, we have one more concept of how we kind of are able to use this in things that we do today. And it's looking at these spectral lines, right? And so what Bohr did is just that. He took an electron, he shot it up, and what he noticed is that as it shot down, he got these colors to come off, right? That's what he was able to see. That's what we're able to see with our eyeballs, right? This is exactly how things like fireworks work, right? Is exactly this concept. All right, and so this is the last concept that we have for today, is this idea of an excited atom, okay? Because this is what was going on through all of this, is exciting electrons in an atom, and with our eyeballs actually seeing what happens. And so we have to look at 2 different words. We have to look at ground state and excited state. Ground state is the lowest possible energy. Basically, that is Bohr's model, right? If you were to draw a Bohr model, Bohr's model is in ground state. And then from there, we can bring in a photon with a quantum of energy, right? And we can excite an atom. And so if this is hydrogen and we shot it with energy, right? We shot it with a photon with the quantum of energy, we could jump it up a level. And depending on the frequency, the amount of energy of that photon, right? We could jump it up to 1 level, 2 levels, 3 levels. All right. That's where we get it. And so remember, atoms want to be lazy. And so the excited state only lasts for a little while. Okay. And so what we get is we get this second half of it. So we get this photon to excite us, but we got to go back down to the ground state, right? And the trick is light's emitted. This is what our eyeballs see, right? When we get this to happen, right? When we get the right amount of energy to get in there, we excite it, we drop it back down to ground state, and what we get is we get that visual, right? We get that frequency we're able to see. We get that amount of energy that comes off because that's a constant, and we just calculated that. And depending on what happens when that photon goes off, we get different colors because eventually every atom has to go back to the ground state. And so that's what we see right here. So now we can absorb certain amounts of energy, right? And depending on, it doesn't have to drop all the way down. Sometimes it can just drop from, you can see over here, level 6 to level 4 or level 6 to level 5. And depending on what it does, depending on the distance of the drop or the amount of energy it's giving back off, we see different colors. And I'm going to show you a little animation with that. But just showing you the shorter the drop, the closer you are to red. The bigger the drop or the more energy, the closer you are to purple. All right, that'll come up later when we do some calculations. So what does an excited atom look like? If this is fluorine, this is exactly how we draw fluorine. It's Bohr model. So if I wanted to excite it, one of the things I could do is I could just take one of these 2 electrons, right? Knowing that level 2 can hold 8 electrons, I could take an electron from level 1 and I could jump it up to level 2, which still has an open hole right here. This guy doesn't have a buddy. And all of a sudden, this atom of fluorine would be excited. Eventually, that electron that I excited, that I gave a red ball, has to go back, right? It's got to go back. And so eventually it'll go back down to level 1. And in the process, it'll give off some energy. Sometimes we can see it. Sometimes we can't, depending on the jump. All right. But that doesn't matter. That's the point. That's how you go from a ground state, which this one is, to excite it, jump it up here, and then drop it back down. So it's this big cycle that we see. Okay. And what we see with our eyeballs is this, right? We get to see these lines. Again, if we were going to do our lab, I have you look for these lines, right? And the bigger the jump from 3 to 1 or 2 to 1 is how we determine our colors, right? The bigger the jump, the closer we get to the higher energy, which if you've looked at science in any fashion, red is a low energy, purple is a high energy. And so when we think of Roji Biv, right? Biv being very, very big, maybe a 6 to 1, and the red or the orange, being something much, much smaller. Okay, going from there. And so we have something that would look like that in our spectrums. And so we get to see something like this, and we'll end with this, is the idea that this is how we know like what stars are made out of. Because we can look at them through spectroscopes, right? And we get to see all these different lines. And you look at all these different atoms, and what you notice is that not any atom is the same, because when you hit it with certain amounts of energy, right, certain atoms, or certain electrons, I should say, within that atom, jump up and drop back down. And what we see is we see these patterns, right? And it doesn't matter if it's a really small atom, right? Lithium only has 3 electrons, but you see the number of lines. Sodium, right? Sodium has 11 electrons, but you only see 2 different lines, okay? And so it doesn't matter on the number of electrons. It depends on what those electrons are able to do with the light that they have. All right, there we go.